Welcome back, AP Statistics. We have an additional topic. We're going to be talking about test statistics, specifically for the 1 proportion Z test. This will not be the only time we talk about test statistics this year, but it's the first time. So there are 2 schools of thought when it comes to hypothesis testing. There's the p-value method, which is the one that we just learned about in the last chapter. And then there is what you might call the traditional method. At least that's what it's called in the other statistics class that I teach. That second method employs something called a test statistic. And that computes the number of standard deviations for whatever sampling distribution we're using of a sample statistic, like p hat, is away from the proposed value for the corresponding parameter, say p sub 0. Right? So that's a lot, but let's look at a formula, okay? Test statistics for the population mean or proportion fit this form. We have a sample statistic minus the proposed value of the parameter, that's p sub 0, divided by the standard deviation of the sampling distribution. So not the sampling distribution of the variable, the sampling distribution of the standard deviation of the sampling distribution. Okay, so it's a special standard deviation. So the test statistic for a 1 proportion Z test is our sample proportion minus the assumed population proportion p sub 0, the value that appears in our hypotheses, divided by the standard deviation for the sampling distribution of sample proportions, which is always some flavor of square root of pq over n. In this case, it would be p sub 0 q sub 0 over n. P sub 0 is our assumed population proportion. Q sub 0 is the complement, as always. So for the last problem that we did, the one that involved baseball from chapter 19, p sub 0 is 50%. That was our assumed population proportion, which meant there was no advantage for the home or away teams, if you recall. But p hat is 0.5319, which meant about 54% of the time the home team won in our sample of 2,430 baseball games. And that's why n equals 2,430. So our test statistic for this scenario would be p hat equals about 54%. P sub 0, our assumed population proportion, is 0.5. And then we would do square root of why the 2.5s? Well, that's because p sub 0 is 0.5, and thus q sub 0, the complement, would be 0.5. Divide that by our sample size of 2,430, square root it, and we get 3.93. What does that number mean? That means that our sample proportion is 3.93 standard deviations from the proposed population proportion. And of course, that is really far. Consider the 68, 95, 99.7 rule. Past 3 standard deviations on one side is basically no man's land. We're almost at 4 standard deviations. That is the desert. Ain't nothing but dunes out there, okay? So this 3.93 not only means that we have a pretty far out sample statistic that would surely be significantly different than what we expect, 50-50 split for home and away teams, but it's also very far to the right, meaning that there is a significant difference in the positive direction, as we can see between these 2 values. So, one thing that we're going to have to do sometimes is convert test statistics into p-values. The way we get a p-value is we apply a little bit of calculus to a test statistic. All right, that's how we get p-values. And by calculus, I mean finding the area between a curve, like this bell curve here, the normal model, and the x-axis. So this area is the same as the probability. You knew that for pretty much the entire year. But we get that area using some calculus. Of course, we can discuss that kind of calculus at an undergraduate level, but you can do that on the calculator pretty easily. All right, so don't need to do calculus for this class, and you can be grateful for that. So, for a one-sided alternative, a p-value can be understood as the area beneath the appropriate model. This case would be the normal model. So the area between the curve and the x-axis beyond the test statistic. Okay? So if, say, my test statistic landed right here, so here's the mean, and here's my test statistic out here, this area right here is my p-value, which is the likelihood that we got data as extreme or more extreme than ours, okay? So thus we would say a p-value is the probability that z, that is my test statistic, is less than sample statistic minus population parameter over the standard deviation of the sampling distribution if we are investigating the left tail. So the p-value is the odds of getting a test statistic that is below the test statistic that we come up with. See the last slide for how to do that. And if we're examining the right tail, like over here, we'd be finding the probability that our test statistic is greater than the test statistic that we found given our data. All right, so what are the odds that we could get a test statistic that is bigger than this? That would be the area on the right. So whether we're investigating the left or right tail, we would be finding the odds of my test statistic z being below or above the test statistic we get in our scenario. So for a one-sided test for the population proportion, we're going to find the p-value for the test statistic z equals 1.38. And we'll assume that we are testing the right tail, right? That would make sense because z is greater than 0. So here's how we would do this. We would use normal CDF and we would be counting standard deviations. And whenever we're just counting a number of standard deviations, we say mean equals 0, standard deviation equals 1. And we would say here is my test statistic of 1.38. And we want to see what are the odds of getting above 1.38. So we go from 1.38 to 10 to the 99, arbitrarily high number. And that gives us the likelihood of p hat being at least 1.38 standard deviations above our assumed population proportion, p sub 0. If you were to type this into your calculator, you would get 0.0838. Now let's look at another scenario, and you can try this one. For a one-sided test for p, find the p-value for a test statistic of negative 2.15 and assume we are testing the left tail. So take a moment, see how you would set this problem up, and see if you get the answer. Okay, I'll assume we're ready to continue. If you need more time, feel free to pause the video. We would use normal CDF and we would say negative 10 to the 99, arbitrarily low number, all the way up to negative 2.15. That tests the left tail, and we're counting standard deviations for our answer, so we have 0 for the mean and 1 for the standard deviation. And that finds the likelihood of p hat being at least 2.15 standard deviations below p sub 0, so an especially low p hat value. All right, and the odds of being this low or lower would be 0.0158. So a little north of 1.5%. Not terribly big odds. For a two-sided alternative, the p-value can be understood as the area beneath the appropriate model beyond the test statistic or its opposite. And that is an important catch to two-sided alternatives, all right? So a p-value for a two-sided alternative is the area beneath the appropriate model, in this case the normal model, beyond the test statistic or its opposite. So say we have a positive test statistic, what would be the odds of getting this far on the right or that far on the left? Or beyond in either direction. All right, so that's a p-value for a two-sided alternative. Thus, we would say the p-value is 2 2, because we have to do this on both sides, so we double the probability that our test value is less than the test statistic I got from my scenario if the test stat is negative. And 2, again, we got to double it because we're working on both sides. Probability Z is greater than the test statistic we get in our scenario if the test stat is positive. Okay? So that is a big difference between one-sided and two-sided alternatives for converting t-stats, test statistics. If I've said test value in this lesson, that's the same as a test statistic. Converting test statistics to p-values. All right, so when we're doing a two-sided alternative, we got to double that probability because a two-sided alternative considers both sides of the bell curve, not just one. So now let's get to an example. For a two-sided test for p, we're going to find the p-value for a test statistic of positive 1.75, which means we'd be finding the area of being, this is not to scale, of course, we're past 2 standard deviations on this curve, but just go with it, being at or past 1.75 on the right and being at or past negative 1.75 on the left, right? That's what we're going to need to compute. So we would say 2 times normal CDF, 10 to the 1.75, 10 to the 99, arbitrarily high number, and we're counting standard deviations. To find the likelihood of p hat being above 1.75 or below negative 1.75. So we take this probability, that probability without the 2 is just the right-hand side. We need the left-hand side too, and because of symmetry, we can just double it. If you were to enter that in the calculator, you would get 0.0801. If perchance you got something starting with 0.04, just remember you need to double the normal CDF. So make sure you multiply your normal CDF by 2, and you'll get it. One more thing before we end the lesson today. This is a screenshot from your textbook about how to interpret computer output. This is something we'll be seeing here and there for the rest of the year. I do want to familiarize you with computer output. So let's look at this and see what it has to say. The test of p equals 0.5, all right? Usually we have a name for this test, and the test would be p equals 0.5. 0.5 would be the value in our null and alternative hypotheses. That's a p sub 0, okay? Now, estimate, what does that refer to? Well, that is our point estimate for a sample proportion. That would be p hat, all right? So p hat is 0.467, okay? This standard error right here is actually a standard deviation, and it's a standard deviation of the sampling distribution for sample means. Okay, so we have a bit of information about the point estimate and the standard deviation for the sampling distribution of p hat. All right, sometimes standard deviation is called standard error. That is a misnomer. It is the standard deviation in this case. All right, so we have a confidence interval in here as well. A 95% confidence interval. In fact, here is our upper and our lower extremity of our confidence interval, the upper and lower limits of the interval. And then we have a test statistic. We should expect a negative test statistic because our estimate is smaller than p sub 0, the value in our hypotheses. And then we would get this p-value right here. And p-value, let's interpret this right here. Probability greater than absolute value of z. If you were to just see z here, that'd be a one-sided alternative, right? But if you see an absolute value of z, that is a two-sided alternative, okay? So if you see that absolute value there, that means we are looking at both sides of the bell curve. If you don't, that means we're looking at one side of the bell curve. And this high p-value here says, yes, there is a difference between these values right here, but the area to the left of our test statistic is still pretty high, so we should probably, very likely, not reject the null hypothesis. And that's how you would interpret these computer output.